My name is Florian, and I work for a company called Flatiron Health. What we do is we build and operate a data platform for cancer research, which is important for the topic. I basically will explain you what we're doing. And before we get started, I want to mention two things. The first thing is, I know it's after lunch, right? I know you're all tired, but if you manage to stay awake till the end, I will ask a question, and whoever gets the answer right wins a Lego set. So that's my my hope that you don't fall asleep. And if you do, don't snore too loud, please. And the second thing is I use a lot of overlays to highlight also code. So I gray out pieces of the slides, and some people try to read this grayed out stuff. It's not readable, don't try it, you will get headache. So, okay, with that out of the way, let's get started with the agenda. The first thing what I want to talk about is real-world evidence. I want to explain what this is and why it matters. Maybe a show of hands, who has ever heard the term real-world evidence before? That's awesome, right? I also didn't hear about this before I joined Flatiron. Then I want to explain you why it's not so easy to generate real-world evidence. Then I want to talk a little bit about feedback loops in our data architecture. Then I want to explain our foundational technology stack. And then comes the main part of the talk. I want to talk about patterns that we implement to accelerate the feedback loops. And lastly, I want to close with an outlook on the impact on what this has on real-world evidence generation and cancer research. Okay, let's get started with real-world evidence, what it is and why it matters. So the idea behind real-world evidence is rather simple. So the idea is that you take data that is already available in databases for hospitals, practices, that is generated when you go to a hospital, to a practice, all the data is recorded about you, to take that data and make it available for research. That's basically what it is. And the reason why you might want to do this, there are a couple of reasons. The first reason is that medical research is, it's not fast, right? I don't want to say slow because it sounds so negative, but it's not fast, right? And expensive. So we, as I mentioned earlier, we operate in the area of cancer research, and developing a new cancer drug costs hundreds of millions of dollars, up to $1 billion, and can take 15 years. So, and how expensive this is, you can see, I think, the beginning of the year, Bayer, so it's a large German life science company, they had to stop the development of a new drug after the third clinical trial, and their stock price dropped by 20%. So this is how huge the impact is. And real-world evidence is faster because the data is available and also more cost efficient. You cannot replace all clinical trials, but you can replace a lot of clinical trials, especially in the beginning of the drug discovery phase. But there are more reasons than just being faster and more cost efficient. Another reason is that real-world evidence captures real-world settings, right? It's not an experiment conducted in a hospital. It's really data from real settings, right? With all side effects that might happen. And related to this is the third reason, which is for me very important. Nowadays, when people get cancer, it's still a very severe diagnosis, of course, but the chances to survive are much higher. Plus, the chances to have come back to a healthy life after the treatment are much higher than 20 years ago. 20 years ago, of course, there was also chemotherapy available, and the chemotherapy killed the cancer cells, but it also killed all the surrounding cells. So that happened. A lot of people who got cured for cancer, they never, came back to their old life. And nowadays it's different, and largely because researchers understood that cancer is not one disease, it's in fact a collection of 1,000 different diseases. So modern treatments are much more targeted. So this is the reason why they're much more effective. But also what happens is that the treatment behaves different amongst different population groups. So it's very, very important in data sets yet you're able to map out different population groups so that you have a diverse population group. And this is much easier to do with real-world evidence than it is with clinical trials that are local to a hospital. Okay. I hope I could convince you that it matters. So, and now I start complaining a little bit about how hard it is. It starts with, I think, this doesn't only apply to real-world evidence in oncology, probably this applies to the whole healthcare sector. It's a mess, right? There aren't really standards in this way. There are 1,000 standards and none of them is implemented till the end. Many systems don't implement any standard. The systems that you integrate, they are not built for capturing, data for research. And if you look at this, so the data we're dealing with, it comes in all different shapes. So files, APIs. Sometimes there's a data exchange format, which is like a whole different ecosystem. There are things like FHIR, HL7. BDT is a German standard from the 90s. It's awful, but at least it's a standard. So meaning there's a 50-page PDF documentation. But most systems, they don't implement any standard. So meaning you also have to integrate internal database formats. So it's a technical, it's a technical challenge. But when you basically start, and you're able to integrate the hospital systems, then you have the next challenge that the data that's relevant for us doesn't sit in a database column. So there is no database column that's called biomarker test result. Typically it's free text field for whatever reason. So most of the relevant data is free text fields or even documents. So it's a lot of natural language processing, sometimes requiring OCR. So this is generated by, it's not real patient data, this is generated, but it's an example, right? It's like free text field. When you go to a doctor, the doctor just types in information into the system and the data stays at this in the system, right? And you have to get the information, they extract the important variables out of that. And lastly, we do all of that in an area which is like strictly controlled, which makes a lot of sense because we're dealing with highly sensitive data, right? So you really need to build a data architecture that is secure and maximizes, let's say, the anonymization guarantees. And to show you how to do this, I will show you now a scary picture. So this is a like 10,000 feet bird's eye view in our data architecture. And which is like foundation why we can do this even in Europe, right? So we basically divide our data architecture into multiple layers. And when the data travels through those layers, it gets more and more anonymized. We start in this gray area, dark gray area. This is basically hospital environments, right, where the data extraction starts. And it depends on the different hospitals, but of course we want to transport the data as soon as possible to our cloud environment. The first cloud environment where we copy the data to is controlled by the hospital. So for people familiar with GDPR, the hospital's data controller, we are a data processor in this environment. There we continue the pre-processing, so pre-processing against anonymization, filtering for legal basis, which is rather difficult, so there are all different regulations on which data you can use. But by the end of that, the data is, we have removed all patient like identifiers, things like insurance numbers, names, addresses, telephone numbers, and things like that. And we have a legal basis for processing the data. So with that, we can transfer the data of the patients into a cloud environment that's controlled by us. There we normalize the data, we transform the data, and we extract the meaning out of the text. And the data sets that we create, then we finally load into a data serving environment where our life science partners then work with the data. We do that because anonymization is a tricky thing, right? So until that point, the data has no identifiers anymore that could be linked to the patient. But if a statistical attack, right, let's say, there's a patient with this kind of biomarker tests and this cancer type between 80 and 90 years old in that region, if you have our data sets, you can, link the data back. So what we do is our life science partners work with the data in an environment that we control so that we make sure that they cannot link the data to other data sets. So I would not expect that anyone understands like this diagram, but at least the message is it's complicated, right? You have, I need a bit of empathy. So, but the second, or like another thing I want to mention is that in the end we're like an IT company, right? So we work in a setting like every one of you. So we deal with iterations, we have sprints, we work in an agile setting. So we try things out, we generate feedback, and then we correct. And in that, and I want to talk a little bit about feedback loops. Because the data we're dealing with is very, very complicated. So before I joined Flatiron, I was working for eBay, and for some years I was working in the marketing area, and it's the data structures I could understand. It's click on a button, right? So account, right? I can understand that. Like biological data sets I don't understand. So really dependent on hello? Okay, perfect. So, so the data sets are complicated. So we have a rather large workforce of clinicians. These are like oncologists that are our domain experts. Of course, we have many data scientists working for us. And then there are people like me, like the engineers who complain about the other two functions constantly and try to keep things running. And those functions have to work together to make it all work. And this feedback loop happens in that environment. So it's like you have different function groups working in a very fragmented system architecture. And I have two SmartyPants quotes. That's my first SmartyPants quote. When you look at the system, this is a socio-technical architecture, right? So why this matters is like the communication flow, how people can work with each other. It's not only defined by the technical architecture, it's also defined by the organizational structure. And by regulations, team structures, technical architecture, you introduce all kinds of boundaries, and boundaries make, feedback slower, or slow down feedback. And so I would say you can improve the agility of such a system by trying to design your core feedback loops in such a way that they cross not so many boundaries. So that's basically, I have a second SmartyPants quote later, but that was my first. So, so these are my thoughts about feedback loops. And let's now look at our technology stack. This is a foundation to explain how we accelerate our feedback loops. So the first thing is we run on AWS largely, right? I mean, as with every company, we have 1,000 examples of the way how we do things, right? But largely we run on AWS. Then we use Dexter for data orchestration. Then we use DLT for data loading and normalization. I will talk about all of this in a second in more detail. Then we use dbt for data transformations, and our data pipelines run mostly in Snowflake. And by the way, this is the motivation why I give all those Lego sets, because I'm incredibly proud of those Lego brick animations. So, okay, so let's build up a data pipeline and start a terminal. The first thing what we do is, so we're using Poetry to add all the dependencies. So we use Poetry to add Dexter, dbt, DLT, and the IBIS framework. Maybe, and then let's have a look at Dexter. Maybe, who of you knows what Dexter is? Okay, awesome, not so many, that's great. So Dexter is a data orchestration tool, like Airflow, like Prefect. So it's a new generation data orchestration tool. Basically, you can build data pipelines with it. And the reason why we like Dexter a lot is there are two big reasons. A, it has a great integration into the Pythonic data ecosystem. There's a lot of good integrations with existing frameworks. And the second reason is that's actually the only data, like professional, like production-grade data orchestration tool that I know that runs without infrastructure. So you can run it as a library. which matters for us a lot. You can scale it up, you can deploy infrastructure, you can deploy a server if you want, but you can start running it locally without a server. Okay, then the next technology, dbt, let's have a look at this. Let me also show of hands, who of you is using dbt? Okay, also great, so that, then I can claim things and nobody can check if I'm correct or not. so dbt nowadays is a lot. What dbt for me is, it does two things. It's basically about SQL development, and it introduces software engineering practices to SQL development. Meaning you can modularize your code, right? You can split up your large SQL code into modules that basically can reuse code, and you can test it. dbt is not the only framework that allows you doing this, and there are maybe nowadays more modern approaches, but dbt is like really a proven tool, and it works for us well. So we use dbt for data transformations, basically writing SQL code for data transformations in a sane way. The next tool that I want to show to you is DLT, which sounds like dbt. Does any one of you know DLT? The really awesome thing is, it's a Berlin-based company, so I'm from Berlin. But so DLT stands for Data Load Tool, and it has the same mindset as dbt. It's a library, right? It's not a SaaS product, it's not a platform, it's just a library. And it's an ingestion tool, so it's a library that helps you to extract data from a database and API, normalize it, and load it into a target system, right? So there are like 5 trends, so like there are paid products on the market that you can use, and DLT is just an open source library. That's my second Smarty Pants quote. The way how I think about DLT is inspired by the history of how we build data pipelines, like the majority of the patterns. When you think like 15 years ago, right, people were building ETL pipelines. So you were extracting data from a data source, you were transforming the data outside of the data warehouse, because the data warehouse was very expensive and compute and storage was coupled, so you really only wanted to load data into data warehouse that was ready. Because this was a tool that was used by analysts and by the stakeholders. And then came the age where compute and storage were decoupled, and the cloud data warehouse came up, the cloud data lakehouses and how they all called, like your Databricks, your Snowflake. And they basically told you, hey, we are fast enough, just give us all the raw data, right, and do all the transformation inside the warehouse. So then we started by extracting data, loading the raw data into the data warehouse, and doing all the transformations there, which is a great thing, because you transform the data where the stakeholders work, which is, of course, faster to change things. But the problem is that this also gets expensive very quickly. And Snowflake is a great technology, but it's an expensive technology. And the approach of DLT is that it says, hey, it makes sense to do a lot of transformations in your data warehouse, but not all transformations. There's a certain kind of transformations that doesn't make sense. And this is the old school database normalization. So first, second, third, normal form. Basically, you take a JSON structure and map it out onto a tabular structure. This you do once with the data, you don't change it, it's not a semantical transformation. And with DLT, you can do this kind of transformation outside of the data warehouse, and like the business-created domain-specific transformations inside the data warehouse. And I heard that they call this ENLT, so extract, normalize, load, transform. So I like this mindset a lot. And for us, in some cases, by moving over to DLT, we actually could cut our our data warehouse costs by 50%, because the normalization of large JSONs is very expensive inside a data warehouse. Okay. The last tool I want to talk about for now is the IBIS project. Does anyone of you know IBIS? Oh, cool. Then same thing, I can claim no things, nobody can check, or basically not while I'm still here. So the IBIS project aims to standardize data frame APIs. So who of you is working with pandas, for example? Okay. So that is like a very common like experience for like data scientists who work with data in Python. And IBIS tries to build the same experience in a standardized way that works with all databases in a way that you don't have to load the data into memory. Basically what you do is you define a data frame, operations, and what it does is in the background, it builds a SQL statement and pushes the SQL to the database. Under the hood, IBIS uses SQL Glot, which is basically a transpiler that transpiles SQL into database native statements. So it's great when you want to write data frame code that's agnostic to the data backend that you're actually using. Okay. These are all the technologies we want to introduce. Then let's start writing some code. So we're writing a Dexter pipeline in a single Python module. So this is typically called a definitions module. So the first thing what we're doing is we set up DLT for extracting, normalizing, and loading the data. And I want to highlight a couple of things. So the first thing we want to do is implementing a DLT transformer. This all is decorator based, so we write a function which we decorate with the DLT transformer decoration. What the transformer function does, it gets file references, so pointers to files. It loads the file and then transforms it in a way that DLT can create nice tables of that. In our case, for example, we take the BDT structure, which is like a German data schema from the 90s, which is line-based. I think only older people will remember how that looked. So it's a text file with a billion lines of rows with, has in the beginning has the length of the line and stuff like that. So what we do is we convert this to a JSON structure because DLT understands JSON and DLT is able to turn JSON into nice tables. Then we combine this into a DLT source. We use the file system function, which is built into DLT, which is basically iterates over storage. In our case, it's an S3 bucket, can be local file system, and basically gives you pointers to all the files in there with backtracking built in. And we pipe this together with our transformer. That's the pure DLT setup. Then we wrap this all, because we want to execute it via Dexter. And in Dexter, like every compute node in Dexter is called an asset. So we basically write an asset function. It's again a Python function, which is decorated with the addAsset decorator. We pass in a reference to DLT, a DLT resource. We use DLT to create a pipeline, and then we use this pipeline to run our source. And lastly, this is a concept of Dexter as well, that we don't need to hard code, the creation of a DLT pipeline. If you do that, it's not so easy testable. Instead, you write a resource, which is basically passed into your function by Dexter. And our resource, like the DLT resource, is rather simple. It has a function called pipeline, and what it does, it creates a DLT pipeline. It's just 4 lines of code. And we basically tell DLT the destination is Snowflake, and the connection credentials, connection information is passed by environment variables. Okay. So now we have a DLT pipeline, which again extracts the data, normalizes it, and loads it to Snowflake. The next thing is we use dbt for transformation. So we now need to combine DLT and dbt. And in dbt, you do this with YAML files. You write a lot of YAML files if you use dbt. We basically need to declare, we need to tell dbt which tables DLT generates. And the way we do this is a YAML file where we specify a source, a dbt source has a name, right? And a list of tables. That's a source. So then you can use those tables in dbt code. And what we also do is we have some meta attributes here. We specify some Dexter asset keys so that Dexter understands that those tables should be treated as assets so that you can run the whole pipeline via Dexter. Else, Dexter would not know about them. So with that in place, now this is like a bit, I would like to not do that, but there is no magic. You still need to declare those dbt sources as Dexter keys. So what we do is there's a code, we read this YAML that I just showed you, we go over the asset keys, and we generate no-op assets. So there's pass. We just do this so that we can declare a dependency between those dbt sources onto the DLT tables. It's just pure for dependency management that Dexter understands the dbt transformations are dependent on the DLT tables. Okay, With that in place, we can start writing DBT code. So we, for example, for the lab table, which contains laboratory tests, we heavily use macros. So that's a feature. This is a feature of DBT that I mentioned, that you can basically write usable SQL snippets. In that case, like as I mentioned, this BDT is a standard, which is implemented by some hospitals. And as soon as a hospital has a standard, and for some variables, we can reuse code to extract those variables. So in that case, for the lab values are rather standardized in BDT. So we write a macro, which then contains the SQL code for the transformation. So all you select from where. So with that in place, now we have our DBT setup. So it's just one DBT model, so one table and one macro. Then we can compile DBT. What DBT now does is taking those templates that I showed you and create real SQL out of that. Compile is a little bit, it's not really true, so DBT does not compile SQL, right? It's a text processing engine. But here we basically tell DBT, compile it against Snowflake, right? We have a Snowflake profile which also contains the connection information. What we get then, we get a manifest file from DBT which contains all the information about the DBT models. And then this manifest file we can use to combine DBT with Dexter. And this is what I mentioned earlier, Dexter has a very nice integration into the Pythonic data system. So the DBT assets it's one of those extensions of Dexter. We basically can create a function, we decorate it with the DBT assets decorator, and we point it to the manifest file that we get by running DBT compile. And with those 3 lines of code, Dexter fully understands your whole DBT DAG and can run DBT via Dexter. The last thing what we want to do now is writing a non-DBT transformation, which we do for our NLP tasks. So this is now pure Python code. Again, it's a Dexter asset. So we write a function, and we want to run this function via Dexter, so it must be an asset. So we decorate it with asset. We make this function, we add a dependency. So this is dependent on DBT. So this runs after all the DBT transformations are executed. We pass an IBIS, right, as like a backend agnostic way to talk to the backend, so in our case Snowflake. We use IBIS to obtain a session, then we create a table expression, so we pre-process the data, filter it, join it, and so on and so forth. And then we load the data into memory in batches, right? Because the table is of course large, we don't want to overflow the memory, so this is like 2 bundles batches. And then each batch we hand off to an NLP task. We get, in that case, this is an NLP task that harmonizes the data, standardizes the drug names and the test results and things like that. And the harmonized rows we write back to Snowflake with the create table or insert statements. And IBIS we handle the same way as we handle DLT. We declare it as a Dexter resource, and all what this IBIS resource really does is, when we call session on it, we create a connection to the underlying backend. In that case, we use the Snowflake backend. So, I need to speed up a little bit. Sorry. So we combine everything together in a definitions object. So we combine all the assets and the resources, and we for the DBT resource we again pass in the Snowflake profile. With all that in place, then we can run Dexter via CLI. As I mentioned, no infrastructure needed, no server needed. You can run it from your laptop. We call materialize, and what this now does is it starts DLT, it extracts the data from DLT, then into memory. It normalizes data into nice tables. It loads those normalized tables into Snowflake. Then DBT takes over, transforms the data inside of Snowflake, and then our NLP task is triggered to do the post DBT transformations, and then we have our final lab table that is used as this in a research setting. So that was a lot, I know, but I see at least not all eyes are closed, so you have a chance to win the Lego set. Very good. Okay. Now I want to mention some of the patterns that we implement to accelerate the feedback loops. The first is testing, but I will skip through this in order to save some time. So it's about writing tests. So it's about data tests. Okay. The next thing we do is we connect pipelines to notebooks to enable rapid prototyping, as people called it 20 years ago. And the idea is that data scientists and clinicians can pair together, can sit in front of a computer or do it via Zoom, and load the whole pipeline into a Jupyter notebook, change some code, run it, and see what happens. So what you basically do is, in the first setting I showed you, our pipeline was executed on EKS, like on a Kubernetes cluster in AWS. So what we basically do is we replace the AWS infrastructure with Jupyter, with a Jupyter notebook. The way how we do it is rather simple. So first we need a new dependency. So we add the IPY kernel dependency, and then we use this dependency to generate from our Python environment a Jupyter kernel. And this Jupyter kernel, we can now open up a Jupyter notebook. Right? This runs in SageMaker and AWS, but any Jupyter installation will do. What we now do is we can load all our definitions, all our assets, Dexter assets, into a notebook. We can override one of those definitions, so we can just write a new function, and then we call this a built-in materialize function from Dexter, and then you can run your pipeline from the notebook. And like this, basically, you can like iterate rapidly in a pair programming setting without having to deploy anything. So that helps a lot, especially in exploration phases. Okay. And the last pattern, so the third pattern, is that we want to make pipelines portable. And maybe the why I will explain afterwards, but the first thing what this means is when you look at this stack, so we already replaced AWS kind of with Jupyter. The non-portable part is Snowflake, right? It's a cloud infrastructure. So basically what you want to do is you want to replace Snowflake with a portable database, which is DuckDB. In order to do that, we first add the DuckDB extras of all the dependencies that we have. So for DBT, DLT, and the IBIS framework, we add the DuckDB extensions. Let's have a quick look at DuckDB. And again, a show of hands, who of you knows DuckDB? Oh, also great, perfect. So DuckDB is not as DBT. DuckDB doesn't try to do everything, I think. So it's very simple to describe DuckDB. It's an analytical database that can run in memory or on a file. So it runs on your machine. And it's a production-grade database, meaning if all your data fits on your laptop, you get the same performance as with Snowflake, and you also have a very comparable feature set. So it's a production-grade analytical database that runs is based on a file. Let's see how we need to change our pipeline to use DuckDB instead of Snowflake. So the first thing is, for the DLT resource, we tell DLT to use DuckDB instead of Snowflake. Very simple, right? That's a simple change. And the connection information is again provided by environment variables. Then comes the complicated part, also why I said that DBT does not compile your SQL. In our case, we were writing a lot of Snowflake-specific SQL. So that's, of course, a problem. It doesn't run as is on DuckDB. What we did in this case, we replaced those functions with macros. So like also toDate is a Snowflake function, which is now a macro. And the way how DBT handles different dialects is that you can provide different implementations depending on the database adapter. So in our case, so there's a dispatch mechanism. So we have a toDate macro that dispatches the actual implementation to a backend specific implementation. And so the DuckDB uses the string print type function. So there are other competitors of DBT that actually compile SQL and that can do this for you. For DBT, you need to write this code yourself. With that change, we can compile DBT again, this time against DuckDB. And then the last, of course, we need to update IBIS. Again, simple. Instead of using the Snowflake connector, we now use the DuckDB connector. Not much changes here. And for the DBT resource, we need to use the DuckDB profile. And the reason why we do all of this is because what we did right now, the data pipeline I showed you was basically distributed across 3 environments. And what with that change, now it runs completely in DuckDB, we can install and run our pipelines completely in a pre-processing environment. It's controlled by the hospital or directly on the servers of the hospital. Meaning we can apply our transformations much earlier in the process for finding out, for example, for identifying cohorts, getting an understanding of how the patient cohorts of a hospital look. Okay. That all, of course, it's interesting to do that, but also, does it make sense from a domain perspective? And I want to talk a little bit, or like 1 minute, about the impact on real-world evidence generation. It's important for us to scale. So, in scaling doesn't mean, yeah, of course, it means more patients, right? Because the more patients, the bigger the cohorts, the more statistical relevant your data is. But also, we need to increase the diversity, and that means integrating hospitals from all over Europe. And to do that, we need to be fast. We need to be able to bring something to the hospital, install it there, see what we get, and then continue with the project. And the result is that I would say Flatiron is by far the leading company when it comes to real-world evidence in oncology. So our data has been used in more than 1,200 publications. It was cited in over 9,000 peer-reviewed documents. But to close this all up, I want to actually take a quote from one of those publications that we can do all of that on a global reach. So that this setting can benefit patients worldwide by ensuring that high-quality real-world evidence informs clinical decisions and health policies on a global scale. And with that, thank you so much for listening. And I have, 3 minutes left, right? Okay. I will start with the question. So, which database do we use to run it locally? So, that was very fast. You can pick it up to me. And now you can ask me any questions if you would like to.
Okay, just a couple of questions. Like, first of all, why DuckDB and not SQLite? Maybe it's a stupid question because maybe DuckDB is just better. I don't know. And the other question would be, can this process be automated in some ways? With I don't know, like scheduled, like to update data, like in an automated manner? And yeah, that's it.
So the first question, why DuckDB, not SQLite? So SQLite is more like a transactional database. So when you really want to aggregate 1 billion rows, it will die, right? And DuckDB is so you should not insert 1 billion rows into a DuckDB file, right? It's more like you should insert the data into batches. But if you want to aggregate 1 billion rows, DuckDB is really good on this. So it's basically those classical why you would use a data warehouse. So you Snowflake versus Postgres also. Yeah, but like I think SQLite was like was an inspiration for DuckDB. And the second question, yes, it can be automated. So so first of all, Dexter has a whole server setup. So you can deploy a Dexter server, and then you have your schedulers, and you can schedule all of that. We actually do this in AWS. We use another orchestration tool to run Dexter inside a Docker container. Use step functions for that. And automation, maybe want to close in our setting, is so we don't run on a schedule because we need to coordinate the data pools with the hospital. So basically we do this every 2 weeks, right? So there's a little bit of a manual, so you cannot just start our pipelines whenever we want. No. Any other questions? Okay.
Thanks for the talk. I was wondering if you can reflect a little bit on GDPR fundamental rights, how messy it gets. For instance, if someone withdraws their consent to participate in the data analysis or right to be forgotten and so on.
That is it's very complicated because the regulation, GDPR is not the only regulation. In a research setting, there are a lot of regulations. So we have lawyers, right, who basically help us to understand what applies there. And of course, the right to be, like, actually we don't get deletion requests, but what happens is that people withdraw their consent. So not everything is consent-based, but some processes are consent-based, and it happens that people withdraw their consent. In that case, we need to delete the data, and actually, yeah, so like a standard, what we also do is there is a central service that basically remembers the patient IDs which are deleted, and you actually can store the patient ID, just the ID of the patient to understand, okay, this should be deleted. And every data pipeline just reads this list to check if there's some data left, and in that case deletes it, in that case. Because like backups are a problem, Snowflake has a time travel feature. So what basically do is we don't go through our backups and delete the data from there, but as soon as the backup is touched, the data is deleted. Okay. Does it make sense?
It does make sense.
Perfect.
Yeah, I realize it's a rabbit hole, right?
Yeah, exactly.
Thank you.
So.
Okay. Any other question? So let's thank the speaker.
Yeah. Thank you so much for listening.